All right, in this video, I'm going to show you another application of the logistic regression, a much more interesting one, which is for recognizing handwritten digits. So the data that I'm going to use for this, again, comes from Kaggle. So go on Kaggle and type in digits recognizer, and it will get you to this page that is actually a competition page, and you'll have three different types of data that you can download: sample submission, test.csv, and train.csv. So if you want to participate in this competition, you have to use the test in order to show how well you have trained your algorithm. But what we're going to do is to just use the train.csv dataset for our purposes in this video. So go ahead and download the train.csv dataset on a folder on your computer where you're going to save the Jupyter file, and make sure that you first have signed in with Google to Kaggle. So once you've signed in, then you can go ahead and download the train.csv dataset. Again, make sure that you are downloading the train.csv dataset and putting it on a folder where you're going to save your Jupyter notebook as well. I'm simply going to save it on my desktop because that is where I'm going to create my Jupyter file. And it's a zipped file, so you have to extract it again and put it on the folder that you are going to create your Jupyter file. All right, now we're ready to go back to Anaconda and open a Jupyter notebook. So again, while you're in Jupyter notebook, go to the folder where you have saved your file, and in this case it was called train.csv. So I see it here, and I know that is a good place to create my new file. Then that is where I'm going to create the file. I'm going to call it the digit recognition with Logit. All right. But before I show you how to do this project, let me give you a brief introduction of how images are basically stored in Python and basically in computer using an example. So let me change this cell to a markdown and then insert an image that would help me explain this to you. Okay. So suppose that what you have here is a handwritten number. In this case, it's an 8. And what we do here is that we first transform this image to a matrix. Any image can be and is actually described as a matrix in computers, because remember, computers can only understand digits, right? They cannot understand images. So how are images stored in a computer? Well, they are stored in the form of a set of digits. So this is one way that we can represent images in computers. We can turn them into matrices. In this particular example, we have turned this into a 28 by 28 matrix, each cell representing a pixel. So basically, we are going to have 784 pixel. The values in each cell of the matrix would range from 0 to 255, and those are the RGB values. So 0 means black, and it goes all the way to 255, which is pure white. And anything in between is going to be the other shades of all the other colors that we have. All right. So In this particular example, you can see that where you have an image of an 8, you can represent it using a matrix in which some of the cells have a value larger than 0, whereas the other cells have say, a value of 0. So at this corner where it is completely dark, there's nothing here, you see that the value of the RGB for this cell is 0, whereas in the cells that corresponds to the lines where indicate the number 8, you have other values being closer to the RGB code for white, which is 255, right? So if you have any image, and that is not limited to the handwritten digits, any image, if there is a picture of yourself, right, all of your Instagram photos can be summarized into a matrix of numbers ranging from 0 to 255. As you can imagine, if you increase the dimensions of this matrix, right, going from 28 by 28 to larger numbers, you're actually increasing the resolution of that picture. And if you go the other direction and decrease the number, so you can have a 4 by 4 matrix, then in that case you are decreasing the resolution of that image. And that is the whole thing that we're going to use. We're going to treat these 784 pixels, these 784 cell values, as independent features that we are going to use in order to predict the label. So think of this matrix as 784 features, and we are going to add one column that is going to be the label, that is going to be indicating what this number is. And the whole purpose is then going to be to use those features in order to classify the observations into 10 classes, and then the classes are going to be 0, 1, 2, 3, all the way to digit 9. So this is a special type of logistic regression because usually logistic regression is used for when you only have 0 or 1s, right? Basically 2 classes. The example that we used before was whether the house in California was expensive or not. Here we have 10 classes. So the special kind of logistic regression that we were using is called multinomial logistic regression. But we don't have to worry about that because everything is built into the Python function. So we just type in logistic regression and it will take care of it for us. All right, let's start by just importing NumPy, Pandas, and Matplotlib just like before. So import Pandas as PD, import NumPy as NP, and import matplotlib.pyplot as PLT. And again, I'm going to have the matplotlib in line in order to make sure that my images are portrayed very nicely in Jupyter. All right, now once you have that, you're ready to go and import the CSV file, and I'm going to call it digits. So digits is basically going to be pd.read_CSV. And the name of the file that we have is called train.csv. And if you have downloaded the file on the same folder where you have this Jupyter notebook, then it will read it without any errors. And let's just take a look at the shape of the digits object. And you see that it is a data set, a data frame that contains 42,000 rows and 785 columns. Remember, out of those 785, 784 of them are the features, and the last one is the target, is the label that indicates what number that is. So let me just go ahead and show you some of the observations in the data. So you see that you have the label. The label is indicating what number it is. And then you have all the pixels ranging from pixel 0 all the way to pixel 783 for a total of 784 pixels. Okay. So that is how our data looks like. So the way that this data is being collected is that they asked people to write down digits, and when they wrote down the digits, they took a picture of it, they digitized it into these 784 digits, and then they asked them, by the way, what is this digit that you have written, right? Is it the 1, is it the 0, is it the 4, is it the 5, whatever it is, right? So the label is the true digits that that handwritten image actually represents. That is the true label for us. So let's go ahead and create our X and Y data sets. Remember, X was the features, right? The capital X. So I just say X is equal to digits dot drop. What do I have to drop? The column label, right? This is the label or the outcome that I have to predict. So I'm going to drop it from the features data set, and then my label is going to be the label column. All right, just like what we've been doing so far for all of these other machine learning practices, right? We define our features and outcome data sets. So let me just comment it and say define features and label data sets. Now, one thing that I want to show you is these images, right? So I just told you that, these pixel numbers or these features together are going to represent an image that is an image of a digit. So let me go ahead and try to show it to you. The very first thing that I have to do first is to reshape this data set into a 28 by 28 matrix, right? So what we have here is just a data frame in which each row is 784 observations, right? What I want to turn it into is a 2 by 2 matrix, basically a 28 by 28 matrix, right? So what I do here is that I create a new data set, call it X2, which is going to be equal to X1, however, a reshaped format of the X or the features data set. And that is by typing x.values.reshape, and you have to type in -1, 28 by 28, 1, right? And once you type this, Python is going to go and reshape this data set into a 28 by 28 matrix for you. So once I type in x2.shape, you would see how exactly this thing works. So once you type in x2.shape, after you've reshaped it, you would see that instead of having 42,000 observations and 784, which was the shape of the X variable, right? You are now going to have 42,000 observations, right? Instead of 784, you would have 28 by 28, okay? This is what actually the reshaping is going to do for you, right? And then we can actually go ahead and plot it using the command imshow. So you just type in plt.imshow or imshow, and then say x2. Let's say that I want to type to plot the first observation. So I type in 0, and then I define a color map, CMap of, let's say, gray. And this is what the first observation is. Now, if you want to look at the second observation, you change this from 0 to 1, and then this is the second observation, and then this is the third observation, and so on. but it would be also to see what is the label for this observation. So I'm just going to type in print this image is, and then add the corresponding label from the Y data set. So if this is the third observation in the features, then the third observation in the label should also be here. So see that this image is 4, and you see that this is 4. Now, if you want to play with this and just look at a lot of different variations, you can use a random number generator. So go ahead and type in from random, import rand range, and then create an index and say index is equal to rand range, and then identify the top range of the random numbers that you want. And because I have 42,000 observation, the top range is going to be 42,000, right? So now, instead of identifying which observations I want to look at, I just say index, which is going to be a random number between 0 and 42,000. So one of the observations in my data set. And then I'm going to add something, just type in print. This is observation number, and then add the index, so you know which observation it is. And now once you run it, every time you would get a different number. So it says this is observation 29,093. The image is 3. This is basically the label for that image, and this is the actual handwritten digits. All right. If you run it again, you would see another observation. So observation 9,144. This is the image, and the true label for that is 9. This is what the writer, whoever is the person that wrote this digit, meant to represent. This is a 9, okay? All right, now let's go ahead and import train test split and create our training and test data set. So just type in from sklearn dot model underscore selection, import train test split, and then we can identify the X train, X test, Y train, and Y test data sets as outputs of the train test split data sets. And the data that you're going to split is the X and Y. So X and Y are the original data sets that we have here, right? X is only including the 784 features, and Y only includes the column label, so X and Y. And the test size, let's say that it is 25%. And I am also going to use the random state of 1984 so that I will get consistent results every time that I run this code. All right. Now, what do we have to do? We just have to go and import the logistic regression from the linear models library. So again, from sklearn.linear underscore model, import logistic regression, and then give it a name. So I just call it logistic. Is going to be my logistic regression function. And then I am going to fit the data set using the X train and Y train data sets. X train and Y underscore train. It will take some time for this to run. and I have a relatively powerful machine, so it may take a little bit longer on your machine depending on the resources, the computation resources that you have. So again, you get the same error that you got in the previous video, but it's okay. It just says that the total number of iterations has reached before the logistic regression converges, but it's fine. You still get your predictions. All right, it's run, but let's go ahead and predict using the fitted model and the features data set for our testing. So what I'm going to do is to say logistic predictions is equal to logistic.predict, and I am going to use the X test data set. So basically, as you've seen in the previous functions or previous algorithms, when you just type in the name of the model and then .predict, it's going to predict the label based on the set of the features that you provided it, and also the coefficients that it has already estimated in the fitting process. And I am also going to create, say, accuracy. I'm going to again call it logistic. Let me just make the prediction, put an underscore here. So logistic predictions and logistic accuracy is going to be, again, just like before, you call in the name of your model and then you score it based on whatever data sets that you want. Here, we're more interested in the testing data set. That's why I say X test and Y test. And before, I am going to create a format for my accuracy predictions, which was like this. So this is going to create in the percentage format, and then put in the logistic accuracy here as well. And let's print it. So I'm just going to say the accuracy of classifications using logistic regression is, and then I add str logistic accuracy to see what accuracy I get. And you see that I get 92%. It is significant, given that this is a very simple logistic regression that we are using, meaning that in 92% of the times, I am correctly predicting the handwritten digit, or classifying the handwritten digit in its own class. But what does it mean in practice? Like, I want to visualize this 92% performance for you by looking at the values in the test data set, their actual label and the predicted label, so that you can have a feel of how well the algorithm is performing. So what I'm going to do, just like here, where I reshaped my X data set, I am going to reshape my X underscore test data set into a 28 by 28 matrix so that I can use the imshow function. So I just type in X test 2 is equal to X underscore test. This is my testing data set, right? Remember, this is the one that I have used in order to make predictions, right? So X underscore test dot values dot reshape. And again, I use the same format, -1, 28 by 28, and then a 1. And what this does is that it goes and reshapes my X underscore test data set and puts it into a X underscore test underscore 2 data set, right? And then I can go ahead and say plt dot imshow xtest2, let's say that I'm going to look at the first observation with the same color map. So this is the first observation in the test data set. And now I am going to create, again, a random number generator and use that for my representation. So instead of manually identifying which observations I want to look at, I want to look at whatever random number it is. So I'm going to type in index 2, and that is going to be Rand's range. Instead of going all the way to 42,000, let's say that I go between 0 and 4,200. Why? Because the test data set is smaller than the total population. So I just go into 4,200, and then here, instead of specifying exactly which number of the observation I want to look at, I just type in index 2. And at the top, I just say print. This is the observation number, and then str index. So when I do this, it says this is the observation number 9,144. Let me just make sure that it's in the test data set. So this one is example. For example, this is the observation number 9,144 in the test data set. This is what the actual image is. And now what we have to do is to type in the actual label and also the predicted label for this. So let me go ahead and start with the actual label. So I just say print. This image represents, or I said the actual label for this image is, and then add the corresponding value in the test data, the feature, the labels data set in the test proportion of our data. So we just type in ytest dot iloc and add an index. All right. So what iloc does is that when you have a one-dimensional column, basically here, which is your y test, you have to use iloc in order to go and represent that particular observation. So it goes to the location of the index, meaning that whichever observation it is, and prints that for us. All right. Let's see. So here says that this is the observation number 9,144 in the test data set. The actual label for this image is 9. Oh, I have to use index 2, not the index, because index is the one that we used before. So that is why we got errors here. So let's see. If I use the index. Okay, so this observation is the observation number 3,904. The actual label is 0, and this is what it looks like. Let's run it again. This is observation 2,869. The actual value for the label is 6, and this is how it looks like, which makes sense. This is a 4. You see that this is a 4. And I run it again, and it says observation 2,173 in the test data set. The actual label is 9, and this is a 9, right? Now, the final thing that is still remaining is what the algorithm has predicted for us. And we can actually go ahead and type in print the predicted or the classification for this image is, and then use the predict function of the logistic model that we've already trained. So we can go ahead and say, use the model name, which was the logistic. So here, I type in plus, make sure that you use the str function. So we have logistic.predict, and what is the features that has to be used in the prediction here? Well, x test, and the particular observation is index 2. Right. Now, the important thing here is that when I want to predict, I'm using the x test, right? I'm not using the x test underscore 2 because that is not going to work, right? They should have the same shape as the data set that you use to train your algorithm based on, right? But when I want to portray the images, then I use the x test 2 here, okay? So just to make sure that you're very clear about the differences between the x test and x test 2. So here is what we have. This is a random observation 2850. This is how it looks like. The actual label for this image is 3. However, the algorithm has incorrectly classified this as a 6. Now let's run it again. This is another number, observation 249. This is how it looks like. And actually, it is a 3, and the prediction algorithm is correctly classifying as a 3, which is correct. They've done a good job. How about this one? This is a 0, and the algorithm prediction is 0. How about another one? This is a 9, and the prediction is 9. See, it is doing a pretty good job. Another one, 7, predicted as 7. Another one, 8, is predicted as 8. Now, how can we quantify this? Well, we can create a very simple confusion matrix to visualize the performance of our matrix. Again, I will put the link to a video that talks about confusion matrix for classification algorithms. Go ahead and watch it if you need more details about confusion matrix. But we can go ahead and type in from sklearn import metrics, and then create the confusion matrix. So type in metrics dot confusion underscore matrix. Okay, so how do we create a confusion matrix? We look at the actual values and compare them with the predictions, right? What are the actual values here? The actual values are in y underscore test, right? How about the predictions? Where are the predictions stored? You remember here, I put them in the logistic predictions data set. So I come down here and type in, copy and paste the logistic predictions, and that would be my confusion matrix. And this is it. Now, it is very difficult to make sense of, so it is better if we can visualize it in a better way. And to do that, I'm going to put this in an object, and I call it confusion matrix. So I put this in an object, and then go ahead and use Seaborn. So I just say import Seaborn as SNS, and we have used Seaborn library before. Once I have it, I can go ahead and create a plot. So I say plot.figure, and I am going to use a size of 9 by 9, or 10 by 10 is even better. So 10, because we are going to have 10 digits on each side of this matrix. And then once we have it, we can actually go ahead and use heat map. Heat map is a function within SNS that is going to create a heat map for us. I have to give it the name of the data set based on which I want to create a heat map, which is the confusion matrix. And I want it to annotate it for me. So I use this feature annotate, ANNOT, and I put equal to true. Then FMT stands for format, and you have to use D, which is going to be the best format for representing the numbers here. You would see it in a moment. And I'm going to use a color map for it. Let me first create this matrix without a color map. So we're going to use the default for you to see. And this is what the confusion matrix looks like. Now, if you want to figure out what color map to use, you can just search for all the available color maps for the PyPlot library on Google. So this is all the available color maps that you can choose from. See that all the codes are given, and there are many examples of how they look like. So you can choose the one that best suits your needs. So I'm going to say choose this one. I'm just going to copy it from here and then go and say CMap is equal to this. And you see that the color map changes. A much better representation for a confusion matrix. And this is fabulous, right? So you see that on the diagonal, you have the true positives, right? Where here, for example, the number 0 is correctly predicted as 0. Here, you have the number of instances where number 1 is correctly predicted as number 1, and so forth. So let me actually go ahead and put the titles on X and Y labels so that it's much easier to understand. So I just type in plt.y label is equal to actual values, actual digits here, and I just type in plt.x label, and I type in recognized digits in parentheses. I say recognized digits, right? So these are the actual digits, and this is the recognized digits. So here, the actual digit 0 is correctly recognized as 0. And what does say this number 2 means? It means that there are 2 instances where the actual digit of 0 is incorrectly recognized as 2, right? There are only 2 instances of that. And now here, when you see 17, let's see what 17 is, 6, right? This is the most frequent mistake. There are 17 instances where the handwritten digit is actually 0, but the computer incorrectly classifies it as 6. And when you think about it, it's quite common to mistake 0 for a 6, right? Now, let's look at some other instances where here we have a 33. What does it mean? It means that there are 33 instances where a number or a digit that is actually 3 is mistaken for a 5, okay? And it is much more common to mistake a 3 for an 8. You see that number 27 means that there are 27 instances where number 3 is incorrectly classified as 8. I mean, think about it. 3 and 8 look alike in many instances in handwritings, all right? So this is how you create a confusion matrix to and visualize it to represent the performance of your classification. And then one last thing that I want you to note is that when you look at the confusion matrix, let me just print it here. So this is the confusion matrix that we had, right, in numbers. Please note that these numbers are the same ones that are represented here. So the first one was 1003. You see 1000 here. Then you had 0213, 0213, and so forth. All right. So that's how logistic regression is used to recognize handwritten digits.